So my name is José de Oliveira. I lead the engineering efforts in autonomous vehicles at Unity. So I'm part of the machine learning team, but I work 100% of my time is allocated on the automotive initiatives. Today we're going to be talking about, it's a clicker. We're going to be talking about synthetic environments for autonomous vehicles development. A little bit of a big name for the presentation, but the topic is also kind of complex in nature and technique. But hopefully you guys are going to have some fun with that. So what's the agenda? I'm going to give you guys a little bit of context. Not everybody is in the autonomous side. Then we're going to talk a little bit about why simulation is important. We are going to cover what is Unity's role on this particular area. What is the strategy we've been pursuing to complete the charter on this. And then we're going to give it up to CVEDIA and get to know a little bit more about the work they've been doing. So starting with the context, a little bit of a refresher. These are the 5 areas that we've been covering in automotive. Product design, sales, service, HMI, autonomous vehicles. Today we're going to be talking about this. This is like a I am here slide, right? I mean, where are you? So we're here in autonomous vehicles. And when we talk about autonomous vehicles, we talk about autonomous systems, and that's how we perceive autonomous or how we represent it, right? Those are 4 different subsystems. Control, planning, perception, coordination. Control takes care of the actions that the car needs to do. Example, braking, accelerating, steering. Planning is what is the navigation part, like both in long term, like going from point A to point B in the city, as well as taking initiatives like, should I overtake this car or not? I mean, so all of this we kind of bundling in this planning subsystem. Perception is how the car perceives the world, how the car gets information about the real world, includes computer vision if you're using cameras, lidars, radars, also localization, and then what is very well used term is sensor fusion, which is getting all those different sensors and putting together in something that the car can actually understand. And then coordination, it's even more important as we are talking nowadays about always connected cars. Is the ability of having, it's deeply connected with planning, but it's how the car behaves in relationship to other cars that are also smart. So understanding the state of other cars, getting into what we call platooning formations in which the cars follow each other in the roads, or swarming, ability of doing smart mergings in highways and etc. So pretty good. So far, so good. I mean, we're going to have Q&As in the end. But if you guys have any questions in between, I think I'm OK if you guys just post it. So question is, why simulation, right? I mean, so you say, why can't we just use cars? Why can't we put the cars in the street, collect the data, train with that? I mean, we're going to get the guys doing. We have all the sensors array. We get all the information. We train our system like that. And you know what? That works for some, up to a point. And there are some companies that definitely started doing this, and eventually they moved into trying to use simulation. And why? Because collecting data is expensive. First of all, ML is at the core of autonomous vehicles, machine learning. And ML is super data hungry. So you're going to have to collect all this data. It's expensive. You have to put the car in the streets. You're going to have to run several miles until you have enough data to train your machine learning models, at least at the state-of-the-art models that we have nowadays. It's possible that tomorrow the need for data becomes different, but nowadays that's the reality. So it's not enough to collect the data. You have to make sure that the car understands what the data is. So there's this process of annotation. So you have to literally go and say to the car, OK, this is a tree, this is a road, this is another car, et cetera, et cetera, et cetera. And you have to do that for every single piece of data that you collect. So that's both expensive and error-prone, because most of the times you're doing that using humans. If you could do that automatically, then you'd have your algorithm right there. So it's like a chicken and egg problem. And most important, the real-world data can only prepare you for what you already seen, right? So that's why I use this image. This image, I like it because people get a lot of different situations when they run their cars in the streets, and they think, okay, we've seen the worst of it, right? The road ahead is super simple, and I'm happy. Until they bump into something like this, right? So those are just pieces of information. I'll let you guys sink in this information a little bit. There's a guy that decided to take a fun ride in a cart in the middle of the road. There's a tank crossing the street. There is a freaking helicopter. And I don't even know what this guy is doing, but I really appreciate he's a very good driver. So all of this tells me that you probably didn't see the worst of that. I mean, those guys, at least we caught on camera, and thanks to the Russians for having dash cams everywhere. But I don't think that's enough to tell us that we've seen everything, right? Quite the opposite. So that's your answer, right? So why simulate? Simulation can get autonomous systems ready for unforeseen scenarios, edge conditions, in a fast and cost-effective way. That's very important. It's not only that it's not sparse, it's not only that you have control over the data generation, but it's also fast and it's also effective, right? And that's super critical. So moving forward, what is then Unity's role on that? It's a big hint. We are very good in generating synthetic data, right? But what does that mean? So this is a typical way of in autonomous vehicles, how we represent the levels of automation, right? That's called levels of autonomous vehicles from 0, which is absolutely no automation, to 5, which is, yeah, your car now is an elevator. It goes by itself. You don't need to care about what's going on. Broadly, this is a little arbitrary, but there is a little bit of a separation in the middle when the critical scenarios stop being handled by the driver and start being handled by automation. That's right there in the middle. I mean, the level of engagement of the automation changes until you get level 5, but that's broadly what happens. So what happens beyond level 3 is that the complex scenarios make it economically feasible for the established methods to be used. So simulation in automotive industry is not a new concept that have been used for a while. The problem is that the simulation as it's standard, based on the solutions that it's standard, was super, super good for very restricted cases. With the advent of autonomous vehicles, the scenarios are, you know, like, oh, you expect a car to behave like a human behaves. Well, that's freaking complex, right? So the black box, you know, shrink-wrapped the solution that you typically used in the past to represent your systems, to train your ABS brakes or whatever, they do not suffice anymore. And that's where Unity plays a role. That's the ideal situation for Unity. Not only because it's a super hard problem, and we love hard problems, but that's because Unity is really well suited for that. So when you think about simulation systems, this is what I just pointed to you guys before, right? This is an autonomous system. Could be the real deal, could be the actual hardware, but when you model the autonomous systems, you also use approximately the same situation. Then on the other side, you have the simulation environment. So what's the simulation environment? So you're going to try to produce to the autonomous system an environment and a set of signals that are as close related to what a real car would see in the road as possible. So there's some communication going on. There are some external databases that can be used to generation of scenarios. And there are, importantly, these different blocks here, right? Let's see, do I have a pointer? I thought I had a pointer. I do not have it. So vehicle dynamics, loosely associated with control, in the sense that this is how the car behaves physically, like a friction with the asphalt and all the sort of things. Then there's the environment, which is like your street, everything that you have in environments. Environments, you know, if you have been working with Unity, you know that there are different kind of assets you can have. So we split them into what we call static elements. You can imagine the roads, trees, you know, stoplight signs, etc. Those are the static elements. They build your scene. Then the dynamic elements, pedestrians, other cars, everything else, they provide you with variations into your scenarios, or a creation of scenarios that can be used to validate or collect data for your vehicles. And then parameters, because on top of all this, you can vary time of the day, weather, all sorts of different conditions that you can apply to that scenario to recreate the situations. And the conjunction of those, these are the ones that allow you to produce the edge cases that you didn't see in reality. For instance, if you go to Seattle, that's my hometown, sort of, probably you'd have a hard time trying to recreate a sunny scene. Right? We don't see the sun there too often. So if you run your car, maybe you get like a couple of days in July with sun, but most of the time it's going to be cloudy and rainy. But if I have a Seattle synthetically in my computer, then every day is a sunny day if I want that to be, right? And then everything that you do in the simulation has to be consumed by the system through the sensor model. So the sensor model is like a LiDAR, a camera, a radar. It has to be physically accurate to the point that your algorithm relying on this information can behave in the synthetic environment as well as it would behave in reality. Otherwise, you have a problem that we typically call the reality gap, which is when you have all your system simulated, and then you're going to go transfer that stuff to the real thing, and that stuff doesn't work. And doesn't work why? Because maybe you screwed up in how you represent the sensors, maybe there's other problems. But it's not an easy problem. It's not say that it's a slam dunk, that everything is going to transfer. But definitely, if you screw up the sensor model, you're screwed. So Unity, again, very good for these areas that I'm setting up there. I mean, the replaying of scenarios, very, very close related to lots of animations that we do in gaming. Creation of environment is a deal, right? I mean, that's what Unity is good at. And the sensor models, all the cameras, all the support that Unity has to do ray tracing, this is a godsend to the creation of environments. And how we build the simulation, that's what we call the workflow. It's a little abstract, but hang with me. We have some like if you read from right to left, right, you start with some sources of data. It could be real-world capture from a sensor. It could be HD maps, high-definition maps. It could be OpenDrive, which is one of the standards. Then eventually, information, and it could be out of your mind. I mean, you could be creating what we call artificial scenes that don't have necessarily relationship with the world. They are representative of the world. You can be building downtown scene that doesn't represent any known city. And that's okay. For some phases of autonomous vehicles development, that's what you want. You want to have flexibility to change into unknown situations, even if those situations don't exist in reality, right? You want to push the boundaries there. So once you have your environment, which is strictly speaking the static part of your data, you start to produce these different scenarios, you start doing the variations, and that's the part that, using things like a timeline and all the traffic models, pedestrians models, this is super good. The stuff that Unity Labs presented last night at the opening speech was really, really interesting. I mean, we are going to be able to really model pedestrians in a very realistic way, and that makes a lot of difference to how real is your simulation, right? And then all this needs to be integrated through sensors, implementation of protocols. In the end, Unity, in most of the situations, Unity is not an end in itself. The simulation is part of a bigger system, and Unity has to behave as a component of the system, which means having protocols to other pieces, enable co-simulation, enable all sorts of different scenarios. Typically, we refer to them when you simulate everything in the same box or only on software. You call that software in the loop. when you have the actual hardware, you put like hardware in the loop, you can go one step further, you have that driver in the loop, but the idea is that Unity needs to be a component. Your simulation needs to be a component of a broader system. And then the rightmost column is the typical applications of autonomous vehicles that take advantage of the simulation. So one would be the training of the models. And models here we are using kind of broadly. It could be machine learning or it could be not machine learning based. It doesn't matter. But you train that based on this interaction that you have with the synthetic data. Then there's a validation. You try out your models. You see if the models are working in different conditions. Certification is a kind of a variation of a validation in my mind. That's a simplification, but which means that a third party, a government, some organization that is responsible to give you the green light to use the car in the streets is running a set of well-defined tests that they can trust and say, okay, your car is ready now. It's not going to kill anyone in the streets that I know of, and your car can go to the street. And then the data visualization is once you have the car in the street and your car is collecting information, is doing stuff, and then all of a sudden gets in an unfortunate situation that you didn't predict, this data should be brought back and analyzed. And what a better way of doing that than having this data replayed within Unity, and you have AR and you have VR, and all of a sudden you are in the scene again, right? That's a very powerful scenario and a scenario that we believe in. So Unity, again, is working towards become the best platform possible for you guys to build these solutions on top, right? So what's the strategy? And that's a good segue into the strategy. So it's Unity building a simulation? No. I mean, we are following here the same approach that we always followed with games and everything. We do not mistake who are our customers. We do not compete with our customers. Our customers, you guys, you are building the simulations. You are solving the hard problems. We are helping you guys solving the hard problems. We have hard problems of our own. But our hard problems are driven by what you guys need to build in order to complete your projects, right? So how can we help the AV developer? First thing is like we have a humongous community of developers. We have to incentivize the community to build environments that can be used for simulation. That's the sensible thing to do. I mean, lots of the tools and assets and developers out there that have been building their whole livelihood out of games, all of a sudden, because they know Unity, they have a complete new area that they can benefit from. This is super powerful. It's powerful for us building the autonomous vehicle solution. It's powerful for them because all of a sudden they have this additional market that they can cater to. So the second part is we build things that we think should be part of the platform, right? We build ML support. I'm part of the ML team for a reason. We have been building, and you guys probably saw the booth for the ML agents down there. If you guys haven't, I highly suggest you guys to drop by and see what we've been putting out. But we've been embedding into the platform tools that allow you to build machine learning models at the core of autonomous vehicles directly in the platform, right? And most important, we have an ecosystem of companies. We are not solving this by ourselves. We are relying on lots and lots of very good people doing their work to make this, make Unity a viable and the best of class platform for development of autonomous vehicles. So as an example of how we incentivize the community, there's always the asset store. Those are a couple of assets that I picked out of the blue, but they are super cool for the generation of environments that we've been talking about. Easy Roads 3D, I've used that also, and it's really nice. And most importantly, in the asset store, you'll see here there's already a part that we've been handcrafting in terms of simulation assets that could be used. This is not extensive. This is not exhaustive. We are still working on having a better way of surfacing these assets to you guys, right? But then how we strengthen the AV support. These are the three pillars if you're looking from above. These are the 3 nodes of the AV support we are looking at. First, as I said, the sensors SDK. So what I'm listing here is not only the 3 nodes of investments, but some of the investments that we believe are necessary that we actually have in our roadmap to produce in each one of these areas. So when you talk about sensors, it's important to think about a unified way of defining the sensors. We call that a sensor SDK. We need to generate startup kits, some content that people can build out of and not starting from zero. We call them reference models. Then there's lots of 2018 plus features coming that will help in performance and all sorts of things. In terms of content, there is the support to open formats that like OpenDrive and things like that. Working very closely with lots of you guys to create these pipelines for data ingestion that will help generate content faster and at scale. And then some content of our own that we can produce and we can give out and can be used from academia. Remember, Unity is all about democratizing. So when you are talking about solving the autonomous vehicles, we are not only solving the problem of the industry, we are solving the problem to come, in years to come, that will be solved by people that are still in the college. We need these guys to start thinking about this problem now. And in terms of integration, there's a whole communication layer that we've been working on, and streamlining the communication between Unity and everything else. Some performance working on Linux, and the ML agents that I mentioned to you guys. So in terms of sample, these are a couple of samples that we've been producing in-house. Some lidars, you know. When I say shaders here, you see on top, there is a scene that we built, but the interesting about that is that we have an algorithm that automatically goes and classifies the objects as they come. So the idea is that if you can produce something like that, anyone can produce their own environment and can put this shader on top and can start generating data easier. And then the typical segmentation information that you have to the bottom. All this content, by the way, we expect to be available sooner or later for you guys to download, and we're going to be announcing when it's time to announce that. Then the Unity ML agents workflow, that's how we work, right? There is a tight integration between all the TensorFlow, Python frameworks to work on machine learning. You set up the environment, you train them, and you also embed the agents, and that's the system. And this is a good example of that, example that I think is like, it's a still game, but it's the closest I can get from autonomous. You have the application of imitation learning. For those not familiar with the term, one of the cool things about having Unity working with machine learning is that instead of having this typical, produce data, use the data to generate my models and etc., you can have this reinforcement learning applied. So you can change the game, you change the state of the game as you play, and the algorithm, the model learns with the new action, and it works based on rewards, right? I mean, so you define what are rewards, what are punishments for the model, and then what are the actions, and then the model goes and trains on that. And I thought this was on loop, so it's going to be a little weird to keep on talking with this stuff not playing, so we're going to play it. So the idea of the imitation learning is that it's a reinforcement learning, so the model is learning out of observing and trying out things, but they also feed out of someone, a human in this case, playing in the same game at the same time. So it's kind of a constraint reinforcement learning. It doesn't try and error on everything. It actually has a kind of a template that it goes. And the idea here is that the machine starts really bad, but as it goes, it learns really, really quickly. That's the real time there, like 34 seconds. So it learns really quickly how to play this. After a while, it's almost superhuman. It also helps that the guy playing this is really good. I mean, I really wanted to see this model learning with me playing. Probably it's going to take much more than this time because I'm not a good player at all. But that's the gist of that. When I talk about ecosystem, I mean it's a super strong ecosystem that we rely on. And these are just some of the companies. This is not exhaustive list, but you can see we have OEMs, we have companies that are focused in content, companies that are focused in sensors. all sorts of goodness here, and we're going to keep on incentivizing this ecosystem to be even more strong as we go, because we believe that's the result. A good example of some of this experiment, this is a video from our friends in the University Autónoma of Barcelona, the CBC Center of Computer Vision. This is not autonomous vehicles. This is smart cities, strictly speaking. So the whole idea here is that we want to train a computer vision model to recognize through street cameras. I'll give you the pause. Wait a second, because I'm in the middle. So the idea here is that you have these cameras in the intersections, and these cameras are learning what is a car, what's the person, and then it's identifying dangerous situations so that the city can turn a dangerous intersection into a safe one before someone gets killed. If someone gets killed, this person becomes statistics. If someone almost gets killed, that doesn't get reported. The idea is that such a system would be able to report that and make that something actionable. What you see here, the original picture, the static picture is a real camera picture. Everything else, everything that moves is simulated. So, man. Okay. So first scene is camera. Everything else simulated, right? And you have your typical segmentation, you have full control of depth, but I just want you guys to take a look how realistic this looks, how good of a job these guys did, and how much the model is going to benefit from getting this level of realism into the training, and now being able to change cameras, direction, change luminosity, change time of the day, change everything. It's super powerful tool. With that, I'll give it to Miguel to start, and welcome.
All right. So, not sure. All right. So first of all, I would like to thank Jose and the Unity team for inviting us to come and give this talk. And I would also like to thank you all for attending this session. My name is Miguel Ferreira, and I'm a senior software engineer at CVEDIA. And today I will be giving you an overview of who we are and what's the global problem we're trying to solve. And then we'll look at some specific problems that our clients have been facing, what solutions we came up with to solve those problems, and how Unity enabled us to implement those solutions. But to understand the here and now, we must first look into the future, and autonomy is a key part of that future. We can see it, coming up in pretty much every industry, and of course, the automotive industry is no exception. Everyone wants a more enjoyable and safer driving experience, and that's what ADAS, or Advanced Driver Assistance Systems, are trying to solve. But in order to reach those L4 and L5 levels in the autonomy scale, the car needs to be able to have a high-level perception of the world around it. So it needs to be able to detect, classify, and track objects. And those traditional algorithmic-based approaches simply aren't up to the challenge. So that's why the entire community has been moving towards neural networks and deep learning with some great results. But those models, they need to be trained, they need to be validated, they need to be tested, and that requires large amounts of data. So, I mean, just imagine you're an OEM and you are trying to build a model to detect obstacles. So you need to take one of your cars, send it out into the real world, equip it with the sensors you are going to use that can add up to thousands of dollars, and then have it drive for days, weeks, and months on end just to collect that data. Then someone needs to go and label all of that data, because at the end of the day, you are training a neural network model. And I mean, once you get the solution you want, you need to validate and test. So you need to do all of that again and again. As you can probably tell, this is a logistical nightmare. So we knew from the get-go that data was a problem, also because our founders were already working and experimenting in the field. And they were feeling the same pain that data scientists normally feel, where most of their time is spent tweaking and managing the data than to actually train the models that do the actual work. So that's why I created CVEDIA, and our first product was a easy-to-use web-based platform where you can manage all of that data in one central place. And yeah, I mean, managing data is useful, but I mean, acquiring high-quality data to begin with is the major bottleneck. So that's why we created SceneCity. So our goal is to help to train, validate, and test neural network and deep learning models by generating synthetic data sets and by simulating environments and sensors. So now let's take a look at some case studies. So let's start with how we helped one of our clients to validate their LiDAR-based obstacle detection solution. So, all right, so our client was using a LiDAR mounted on top of the car, and they were trying to detect obstacles around the car. And they were doing this on a highway environment. But they were having problems. I mean, testing their solution was extremely expensive and dangerous. They had to go out into a real highway and test it out. And so they were looking for an alternative. So that's why they contacted us. And so it set out to solve this problem by simulating the environment that our client was operating on and simulating the sensor that they were using. This, of course, posed some challenges, the first of which was the environment. And for that, we created a 25-kilometer highway loop that acted as a sandbox where those tests would be performed in. And this is where Unity's asset store was critical, because we could use plugins such as Easy Roads to build the roads and Map Magic to create the environment around those roads, and take something that would take us perhaps months to create from scratch and do it in just a couple of weeks. So now having that environment, we needed to populate with a wide range of vehicles, from trucks, motorcycles, buses, and so on, because each one of those vehicles results in a completely different response on the LiDAR sensor. We then created a traffic simulation that was extremely flexible to fit the needs of our clients. And for the main car where the sensor was mounted, we had two driving modes. We had the auto driving mode and we had the manual driving mode. If it was in manual driving mode, our clients could drive the car using keyboard, a joystick, or a steering wheel. And now that we have the environment and that we have the elements to populate that environment, we need to come up with a way to generate those edge cases that are so hard to come by in the real world. And that's where our API comes into action. So our API is a thin scripting layer that sits between the simulation and the end user, and it accepts a wide range of commands for creating, positioning, and configuring objects. So, I mean, in the image you see there, you have, we just load the highway scene and we place some animals in front of the car that allows us to reproduce an edge case that is super hard to come by. And that's where, Unity's component system was extremely helpful, because pretty much all of our commands are a one-to-one mapping with Unity's internal logic and hierarchy. So now that we have the environment, we have the objects and we have the ability to create those edge cases, we needed to simulate the actual sensor. So in this case, we're simulating LiDAR. And LiDAR stands for light detection and ranging. And the LiDAR that our client was using was a spinning multi-beam LiDAR. So if we think at the photon level, each one of the photons emitted by the beams goes out into the world, it's an object, and then it can return back to the sensor. So based on the time it took for the photon to go and come back, the sensor is able to estimate the position of those objects. Since we have multiple beams in the vertical pattern and the sensor is constantly spinning, we can get a 360 view of the world. Of course, one of the great things about LiDAR is that it is unaffected by lighting conditions, so it works equally well during the day or at night. And of course, the ideal solution here was to implement a pure ray tracer to simulate the path that the photon takes, but at least right now it's not really feasible to do that at runtime. So we approximated the same effect by sampling from the depth buffer. So we have a 4-depth-only camera layout to get a 360 view of the world, and then we sample from those individual depth buffers into a final texture. So we stitch those textures using a spherical projection mapping into that final texture. And by sampling different areas of the depth buffer and by changing the input texture resolution, we were able to reproduce pretty much every kind of vertical beam pattern that exists out there, and also to reproduce those accuracy and precision problems that you normally find in the physical sensors. And the result of all of this was a point cloud, or a set of points in space. But we needed to be able to replace the physical sensor by our simulation. So we needed to convert that point space to the same data format that was used by the LiDAR that our client was using. And that's where compute buffers were extremely useful, because we could just take that data and convert it to the data format we needed at runtime without any hiccups or delays. And so the video I'm showing you here, we have at the right-hand side a preview tool created by one LiDAR manufacturer whose main goal is to preview data coming in from the physical sensor. But in this case, we are feeding it data ourselves from our simulation that is running on the left-hand side. And I mean, if you looked at data from real world, you couldn't really tell the difference. So this is our LiDAR simulation in action. Also worth noticing here is that we are not only simulating the LiDAR, we are actually visualizing the resulting point cloud inside our own simulation as well. So by doing all of this, we were able to reduce the iteration times of our clients from weeks to hours. Our client was able to identify and handle new edge cases that they weren't even considering, which all means that their obstacle detection quality improved considerably. And also, since each one of those scenarios is a command set on our API, and since one of those command sets is just a text file, our client could refer back to those files every time they introduced a new change or improved the system to make sure that they didn't introduce any unexpected problem or bug. All right, so let's go through our second case study. This one differs from the previous, as in the previous was all about validating an already existing solution, and this one is about creating a solution from scratch. So our client was trying to build a classifier for detecting pedestrians based on thermal imagery. And they were doing this on a neighborhood environment, but they were having some problems. Their model was performing poorly, mostly because they have a limited training data set to begin with. And it was very hard to go into the real world and gather more data. It was extremely expensive and time-consuming, and the entire labeling process was very, very error-prone. So they reached out to us to see if we could help, and we set out to solve this problem by generating synthetic data sets that then we could combine with the data set that our client already had to improve their model's performance. So, and the key thing here to understand is that neural networks require entropy. So we needed to be able to generalize and to understand what a pedestrian is and what it is not. So we needed to have highly varied environments and people, pedestrians. So to get that pedestrian variation, we used Unity's skin mesh render and blend shapes features, and we created several extreme body types. Each one of those body types was a different blend shape, and then we would just blend freely between those blend shapes. But also, pedestrians are unpredictable. They could be doing all kinds of things. They could be walking, sitting, climbing, and for that we came up with our own random pose system. And this is where Unity's humanoid avatar system was really great, because we could just take any kind of motion captured animation from external sources, use it as an animation clip, and then by using Playable API, we could just, play any one of those animations, jump to a specific time, and pause to get those random poses. But, pedestrians are just one piece of the puzzle. We needed to actually get the wide range of elements that you normally find on a neighborhood environment. So we needed to create cars, traffic signs, trees, and so on. And that's where Unity's asset bundles were critical, because they allowed our art team to keep on creating amazing content in parallel to the development of new features by our dev team, and have the asset bundle as the central place that could be accessed by both parties. So now that we have the pedestrians and we have those elements, we needed to then generate highly entropic environments based on those elements. So that's where our spawner system comes in. So our spawner system allows you to, for a given class of elements, say cars, trees, or traffic signs, to procedurally place them in the world following any kind of pattern. So you could have grids, you could have splines, or any arbitrary shape. And since all of this is easily created and configured in our API, and since our API is just a bunch of text, you could store all of this command set in just one text file and run it over and over again to get completely different results. So now that we have everything we need, we have the environment, we have the elements, we need to simulate the sensor, which in this case was thermal. So thermal captures mid to long wavelength infrared radiation, which is closely related to the thermal temperature of the bodies. And it doesn't require visible illumination to work with, and it produces high-resolution images. And we are working closely with FLIR, which is the largest thermal equipment manufacturer in the world, to prove the viability of the sensor and to show that it will be one of the most important sensors for ADAS and the autonomous vehicles in the years to come. So to implement thermal, of course, replacement shaders were the obvious choice. For most cold bodies, like buildings and trees, we actually used the albedo color and just went from there, and we could get some amazing results just by using that. But for the most challenging cases, like humans and cars, we ended up creating textures that represented the heat distribution on those bodies. But each one of those textures was just one possible distribution. So we needed to also come up with entropy at the thermal level. So we enhanced our shaders with additional properties like the median temperature, the bandwidth, the variance, and then expose those properties to scriptable objects that then could easily be accessed and modified by our API at runtime. So now that we have those highly entropic thermal frames in place, we needed to have a way to label that data for the machine learning to be able to learn. And that's where our segmentation camera comes in. So our segmentation camera is able to take each one of those frames and get a per pixel segmentation map for all the classes we are interested in. And since all of this can be created and configured through our API, and since our API are just a bunch of text lines, it also meant that we could easily create a Python wrapper and send those commands over. So our client was already using Python to do their data set generation, so they could just easily integrate our workflow into theirs. So yeah, in this video we are showing our synthetic data set generation on the right-hand side that is being driven by a Python script that is running on the command prompt on the left side. So by doing all of this, we were able to improve our client's thermal classifier to get higher precision and recall ratios, meaning that it was able to detect more pedestrians and make less mistakes, and to achieve a higher degree of confidence in those predictions. So the video I'm showing you here is their model after being trained with our synthetic data sets trying to predict where the humans are on real-world images. So the green boxes are the ground truth that was manually labeled by human, and the red boxes are the detections that that the model is doing. And I don't know if you can tell, but we were able to detect pedestrians in many instances where the human wasn't able to. So, and all of this that I'm showing you is just the tip of the iceberg. I could talk about the way we implement RGB cameras, the way we do aberrations and fisheyes. I could talk about how we implemented our radar, IMU, GPS, or how we integrate with ROS. But at the end of the day, and the main point of this presentation, is to show that Unity enables us to enrich real-world data sets with synthetic, to identify and reproduce edge cases that are hard to come by, and by doing so, we are able to increase models' performance and confidence. And by doing all of this, we're able to push the entire ADAS and AV community forward to the next step. So if you are interested in joining this industry-changing movement, just come to our stand and talk with us. And that's it. Thank you. Thank you. Not sure if we have some time for Q&A.
I'm not sure if you have time. I think we are right on time. OK, we take one.
So we saw the example where you said for thermal classification, the client had about an image set of about 2K images, and he was getting a certain accuracy. Would you be able to say that after the data set generated via Unity was given, what was the increase in accuracy from what was it before and what was it afterwards?
Yeah, I can't really disclose the actual values because we're under an NDA. But you know, we were able to get, I would say, in about 25 to 30% better in terms of precision and recall performance ratios.
Yeah. If you guys want to ask us any questions, you guys feel free to get in the booth. I really wanted to thank CVEDIA and Miguel to be here. They are excellent partners. We've been super excited with the work they've been doing, and I hope you guys got a hint of what these guys have been doing, which is excellent. Thank you guys so much.
Thank you.